Well, thank you. I'm very honored to be in this one-word PD seminar, and I'm glad to see so many of you from all around the world. And in fact, I need to be careful because this is John work with Jun Chen Wei, and I saw him on the list somewhere. So anyway. Okay, so I will talk about the Allen-Cahn equation on surfaces, but maybe before this, what I will do is that I will give some kind of very simple overview about what we are working on, and then I try to explain to you what was the problem, and I will not explain to you exactly how we got to the result, because in fact it took us a very long time to realize that it was very simple. So to start with, let's imagine that you have a compact manifold, which with a metric G, and it's n-dimensional. Okay, so here, and you have what is called a double weld potential. So this is a function which I will call W. And so it takes values in 0 plus infinity, and basically it has two minimum, which are usually taken to be -1 and 1. And the prototype is just 1 minus u squared, everything squared. Okay, does the job. It's symmetric. It has all nice properties. So you can take other double potentials, but this one will do everything we want. Okay. So then, so the Allen-Cahn equation are the critical points of some energy, and this energy depends on a parameter. Okay, so this is here, and this is epsilon. So this parameter epsilon, you see, it is distributed to the energy is split in two parts. There is the Dirichlet energy of a function u, which is defined on my manifold, and then there is W of u, which I integrate over the manifold also. And then there is this parameter epsilon that appears twice. It appears in front of the Dirichlet part of the energy, and it appears also like 1 over epsilon. Okay, so you're looking for critical points of this energy, and basically this looks very easy because this energy has all all the good properties, and in fact, you can minimize the energy. But if you minimize the energy, unfortunately, what you end up with are the constant solution equal to -1 or +1. And it's very easy to see that there is another critical point, which is the constant solution, which is equal to 0, the constant function equal to 0. Yeah, so minimizing the energy is very easy. So basically, the idea is to find other critical points, which are not minimizers, but obtained differently. Okay, so what should I say also? As the parameter epsilon, so when the parameter epsilon is very large, in fact, you can check that these are the only critical points, these constant solutions. But when the parameter epsilon tends to 0, then you find more and more critical points. And so the idea is to try to understand these critical points. Now, in this energy, there are two parts. There is the Dirichlet energy and the potential one, so W of u. And you see that W of u is the function which I have taken to be 1/4 of 1 minus u squared squared. So basically, since there is a 1 over epsilon in front of this part of the energy, this will force the solution u to take the value either +1 and -1. And the first term here will basically force the solution to go smoothly from the value -1 to the value +1. So what you expect is that as epsilon tends to 0, the solution, they look like functions which are almost equal to +1, -1, almost everywhere, or close to +1 or -1. And there is a transition region where the function jumps from -1 to +1. And since the energy in this case is more or less proportional to the size of this transition region, this will be linked with minimal surfaces or minimal hypersurfaces in general. Okay, So let me give first the old existence result, which I have obtained a long time ago. And so the situation is the following. So you have your manifold. So I have drawn a manifold, which is a surface of genus 2. And what I do is that I take an embedded minimal hypersurface. So in this case, if I'm in 2 dimensions, this is just a geodesic, okay? Right, so this is the geodesic sigma on the picture, but in general, it could be an embedded minimal hypersurface. And the only thing you ask is that sigma is the 0 set of a smooth function whose 0 is a regular value. So basically, there is a function which is smooth that takes value which is negative on one side of sigma and positive on the other side of sigma. In other words, we say that sigma is two-sided. So here I should have said that this was phi negative and here phi positive. Okay. So this sounds reasonable. And then the result is the following, which I obtained with Manuel Rittore. The result says that for all epsilon small enough, you can find a critical point of the energy. So remember that the energy depends on epsilon. And the 0 set of this critical point, in fact, is a very nice hypersurface, which is extremely close to sigma, and in fact converges to sigma in any good topology as epsilon tends to 0. Also, what you can check from work which was done later on is that the Morse index of these solutions here are in fact are equal to the Morse index of the minimal surface. So when I say when I talk about the Morse index of the critical point, this is just the index of the critical point as when you look at the second variation. And when I talk about the Morse index of the minimal surface, this is again the index of the second variation of the area functional about the minimal surface. So the number of direction over which this second variation are negative. Okay. Right. So this sounds to be quite simple, and in fact so this was not exactly the first time this type of construction was done. I think there was a former construction by Mike Kowalski before in dimension 2. But basically the idea is that, you're going to look for a solution whose 0 set is a normal graph over your minimal hypersurface. And for some smooth function, and in fact, it turns out that if you do all the analysis, basically the smooth function is extremely small. And for example, has L infinity norm, which is of size epsilon square, as epsilon tends to 0. So for people who are not experts on this, what you have to understand is that in this framework, the solution you get is almost equal to -1 almost everywhere on my manifold. It's almost equal to +1 on the other part of the manifold, and there is a transition region from -1 to +1, and the size of this transition region is basically a tubular neighborhood around sigma of size epsilon. Okay, so how much we had to move the 0 set from the minimal surface to the 0 set of u epsilon is size epsilon squared. So to prove this result, there is it's by now quite it's quite technical, but it's doable because a lot of people have worked on this and techniques have evolved. So what you start to do is that you start to cook up an approximate solution, then you try to perturb this into a solution of your equation. And to build this approximate solution, what you do is you start with an entire solution of the Allen-Cahn equation in dimension 1. So in dimension 1, this is just an ODE you have to solve, and you're looking at a function h whose second derivative is equal to the derivative of w applied to h. And it is very easy that there exists such a solution that tends to -1 at minus infinity, +1 at plus infinity. And in fact, for the potential I have taken, this solution is given explicitly by hyperbolic tangent of t over square root 2. Okay, so this is a function that goes from -1 to +1, and there is some kind of transition region around t equals 0. Okay, now the next ingredient is that in a tabular neighborhood of your minimal hypersurface sigma, you're going to use Fermic coordinates. So Fermic coordinates are not so hard to understand. What you do is that you pick up a point, P, on sigma, on your hypersurface, and then you are going to parameterize a neighborhood of sigma by using the exponential map. So you are going to flow along the geodesic that starts from P and has velocity, the normal vector field to sigma at the point P. Okay, so you flow until time t, and so this gives you a nice description of a tubular neighborhood of sigma as a point in sigma, and then t belongs to some small interval, let's say minus delta delta. Okay. Right. So using this, so what you have to imagine is that close to sigma, you have this parameter. P is a point on sigma, your minimal hypersurface, and t describes the sign distance to sigma, in fact. So you're going to look for a solution of the following form. So we are going to choose our heteroclinic solution. Remember that this is the solution of the entire, this is the solution of the Allen-Cahn equation, which is defined on R. So this is the hyperbolic tangent of the variable divided by square root 2. And then, so we are going to scale it by a factor epsilon. So we are going to choose t minus some function zeta of p divided by epsilon. So roughly speaking, this function zeta of p will move the 0 set from when zeta is equal to 0, the 0 set of the function u epsilon is exactly equal to your minimal surface. But when zeta is not equal to 0, then this means that your 0 set is a graph over sigma for the function zeta. And then, so unfortunately, the plugging in the heteroclinic solution is not enough to produce a solution, so you have to perturb it. And the way you're going to perturb it is by adding some very small function. Well, you hope that the function is very small. And depending on these two variables, the variable p, but also the variable t, which I translate by zeta of p. Okay, so here you see that the unknown to solve the equation are both the function v and the function zeta. And in fact, this looks a bit too much. But in fact, there is a technical reason why you need to do this decomposition. And to recover exactly the right space of functions, what you have to impose is some orthogonality condition on the function v. And you are going to impose that at any point of sigma, if you integrate the function v or and then multiply by h prime, then this is equal to 0. So here I cheat a bit. You should not integrate over r, but you should integrate over minus delta over epsilon, delta over epsilon. Okay, but let's, since epsilon will be very small, minus delta over epsilon, delta over epsilon will cover almost all r. And you can check that the derivative of h decays exponentially fast. So this was a small mistake, but not that much. Okay. So you have this orthogonality condition to you have to impose on the function v, and then basically you plug this into the equation and you try to find the function zeta and the function v such that you can find a solution of the Allen-Cahn equation. So critical points of the function, and this is exactly how it works. So here I skip the the technical details. You have to cook up a function space, blah blah blah, but this is not so difficult by now. Okay, So this was the first result. So this produced a lot of critical points of the Allen-Cahn functional once you know minimal surfaces. And a lot of people have been interested recently in going the other way around, namely try to find critical point of the Allen-Cahn functional, and then by variational methods quite involved, and then try to pass the limit to find minimal hypersurfaces. Now let me go back to what I call multiple transition layers. Okay, so now the situation is the following. I still have my manifold M, and this time I have, so for the purpose of the talk, I've drawn a picture of a two-dimensional manifold. And what I have inside my manifold is an embedded two-sided minimal hypersurface, which I call sigma here. So this is the red guy. So I drew a geodesic, okay, on the two-dimensional surface. I assume that it is non-degenerate, and then I assume that there is a condition here. And the Ricci curvature applied twice to the normal vector to sigma plus the norm of squared of the second fundamental form of sigma, I will explain where this comes from, has to be positive along sigma. So the hope is that maybe you can find solution of, so critical points of the Allen-Cahn equation with zero set. In fact, this time will be two graphs over sigma. Okay, so there are two normal graphs over sigma. And as the parameter epsilon tends to 0, these two normal graphs will converge to sigma. So we say that in the limit, what you get is a minimal hypersurface with multiplicity 2, because there are two graphs which are the zero set of your critical point of the Allen-Cahn equation, which have converged to sigma. So the hope is that these two graphs are small over sigma. So these are two hypersurfaces which are, very close to sigma. So they share the same property. Okay. So there is a result by Manuel, Mike Kowalski, and Jinshin Wei, and this result says, so I simplified a bit the result, but this in essence, this result says that there is a sequence of epsilon that tend to 0, and there is a sequence of critical points, which I call UI. Okay, so epsilon I tends to 0, UI is a sequence of critical points of the energy with parameter epsilon I, whose zero set converges with multiplicity, in fact, not only 2, but any k larger than or equal to 2 to sigma. Okay, and so this is some kind, this theorem is much better than the previous one, because not only it recovers the previous result, but also you can have many transition layers of your solution that converge to the same minimal hypersurface. One piece of information also is that the Morse index of this solution tends to infinity as epsilon I tends to 0. Okay, so you can control, in fact, the energy of this solution, but the Morse index tends to infinity. Okay, so I will say a word about so one slide or two about the proof. So I'm cheating a lot here, and basically at the beginning the proof looks exactly the same. And then, unfortunately, you run into many technical problems which were not present in the previous result. So let's say for k equal 2, so you want two interfaces. 5 minutes of thinking tell you that you should look for a solution which is close to something you will cook up using, again, what I've called the heteroclinic solution. So remember that h of s was nothing but hyperbolic tanh of s divided by square root 2. Okay, so, and this was a solution of the Allen-Cahn equation on R. So what you are going to do is that you are going to use this and translated in such a way that the zero set is described as the normal graph for a function which I call zeta1, and there is another zero set which is described as the normal graph over my minimal hypersurface, but now for another function which I call zeta2. And then there will be a small perturbation, and I hope to be able to find zeta1, zeta2, and v in such a way that, well, the first line here is slightly perturbed to produce solution of the Allen-Cahn equation. Again, I need to choose some. I need to choose v, solving some, satisfying some orthogonality condition. And these orthogonality conditions are essentially the same as the one I have presented in the previous result. But I need to have this orthogonality condition for when I multiply my function v by the derivative of h and center it at the point zeta1, and same thing at the point zeta2. So now I have two sets of orthogonality condition, and this should work for any point in my hypersurface sigma. Okay, so at this point you do, and this is the new thing, is you do some formal computation, and once you do formal computation, you find out that, well, to get a good approximate solution, you need to choose the function zeta1 and zeta2 in a very nice way. And in fact, you need to choose zeta1 is equal minus zeta2, and will be like epsilon times some function phi. And formal computation tells you that it should be good if you could solve this equation here, epsilon squared times j sigma of phi is equal to a constant, which I have squared to show you that it is really positive, this constant, exponential minus 2 phi. And what is this operator here that is coming out? This is just what is called the Jacobi operator. This is the linearized mean curvature operator about the minimal surface sigma. So this operator is nothing but the Laplacian on sigma, and there is a potential. And this potential here has two terms. One term is what is called the square root, the square of the second fundamental form of your minimal hypersurface sigma. And the other one is the Ricci curvature of the ambient manifold M applied twice to the normal vector field along sigma. Okay, so roughly speaking, you need to solve this equation, and this equation has been christened to be the Jacobi-Toda equation, and I will probably return to this later on, because it involves the Jacobi operator, but also because if you forget about this term here, this looks very much like an equation which is called the Toda equation. So, so if you were able to solve this equation, eventually you can prove the result. So to prove the result, what they have done is that they have, if I understand well, is that they have slightly rewritten the equation as follows. So in fact, they have put the term on the involving the Laplacian on the right-hand side. And then they have considered that, well, there should be a solution of this equation. At least you can cook up a very good approximate solution to this equation by using an iteration scheme and considering this term here as a small perturbation compared to this term here. Okay, so you can run an iteration scheme. Once you know what is phi j, then you can find phi j plus 1, and you can check that you get closer and closer to solution, and you find out that phi j in fact starts with some constant that does not depend on the point on the minimal hypersurface, and then you have other terms that depend on the points of the hypersurface. Okay, right. So this was basically the main ingredients and the main idea. Then there is a lot of technicality, and probably I have no time to tell you about one thing you have probably not noticed, that this result here only holds does not hold for all epsilon tending to 0, but does only hold for a sequence of epsilon I tending to 0. This is because there is some kind of resonance phenomena that you have to avoid some gaps in the sequence of epsilon. And so and that's the reason why I didn't state the result as saying that there, for all epsilon small enough, there exists a critical point. Okay, so this was very good. And so at the end of the day, what you get is, well, you get exactly what you expect, is that you get solution whose nodal set are two nodal graphs over the minimal surface, hypersurface sigma, and the size, the distance between these two nodal graphs is something like epsilon log 1 over epsilon, if I'm not mistaken. Okay, now, so we were very pleased with these two results, and like 2 years or 1 year ago, there was a result by Otis Shodosh and Christos Montoulides, and what they have been doing is that they have been trying to understand directly the critical points of the Allen-Cahn functional by using some min-max procedure, min-max argument, and then starting from this, they are studying these critical points as epsilon tends to 0, and they try to prove that they get a nice minimal hypersurface or surfaces in this case. So what they prove is the following. They prove that if you start with a 3-dimensional manifold, and if you take a bumpy metric, so bumpy metric is essentially something that tells you that there is a dense set of metrics on your manifold for which all minimal surfaces are non-degenerate. Okay, so this was proven by Bryant White a long time ago. So basically, this says that you're in a regime where you don't have to worry about the degeneracy of your minimal surface. Then what they proved is that if you have control on the energy of your solutions as epsilon tends to 0, if you have a control on the index of your solution, then in fact you have a very nice convergence of the 0 set of your critical point, so solution of the Allen-Cahn equation, and it converges to sigma with multiplicity 1. Okay, so basically this result in dimension 3 is a very nice counterpart of the result of the last result I've talked about, because in the last result I've talked about the index of the solution that were built was tending to infinity as epsilon tends to 0. Okay, but if you have control Morse index and control energy, then basically the 0 set of your solution converges to the minimal surface very nicely. Okay, and so we started to work on this, but for surfaces, on surfaces. Okay, so now on surfaces, we will see that the situation is very different. And in fact, this result here of Shodosh and Montoulides is not correct anymore on surfaces. So you can find solutions of the Allen-Cahn equation whose energy is controlled, whose index is controlled also. And as epsilon tends to 0, the 0 set will converge to a minimal submanifold. In the case of surfaces, this will be a geodesic with multiplicity, let's say 2. Okay, so so now we are on a surface, and so the minimal hypersurface is now a geodesic. So I will take gamma to be a closed embedded geodesic. And then what we will do is, at the end of the day, what we will do is exactly start from the proof of the previous theorem. So what I've tried to explain in the previous theorem is that if you're able to solve the Jacobi-Toda system equation, then what you get is that you're able to find a solution of the Allen-Cahn equation or critical point of the energy. So in our case now, the case of surfaces, and my minimal hypersurface is just a geodesic. The Jacobi-Toda equation is very simple. It looks like this, much simpler. So now it turns out that the square norm of the second fundamental form is equal to 0. And it turns out also that the term of the Ricci curvature is nothing but the Gauss curvature on your surface. And here what I have done, since I have an embedded closed geodesic, I have parameterized the geodesic by arc length. So the derivative with respect to S is just the derivative with respect to arc length along my geodesic. So the question is, can you find solution of this ODE, in fact, now, when epsilon is small? So eventually you can do it when the curvature is constant, but most of the time the Gauss curvature will not be constant. So you have to be careful that the Gauss curvature here is not constant along C. Okay. So it turns out, so it took us a long time to realize that, but unfortunately, maybe too long, I don't know. But it took us a very long time to realize that there were solutions of the Jacobi-Toda system, which can be described in the following way. So here, this is the Jacobi-Toda system, the Jacobi-Toda equation. And remember that S is the arc length along the geodesic. So S goes from S equals 0 and up to the length of the geodesic, which I will call gamma, not gamma here. And so we are looking for periodic solution of this ODE. Okay, and remember that the Gauss curvature might not be constant. So we realize that there are solutions of this ODE when epsilon is very small. There are solutions, and there is two regimes. There is one regime of the the graph of the solution looks very much like the white curve. And in fact, there are two regimes. There is a regime where basically the term on the right-hand side can be neglected. So it's much smaller than any of the terms on the left-hand side. So basically, the equation that governs the solution is this one, which is linear. And there is another regime where basically this term here can be neglected. And in fact, what you get is this time that the equation that governs your solution is almost second derivative of phi is equal to exponential minus 2 phi. And this is the reason this is called the Toda equation. Okay. So solution of the Toda equation are explicitly known. So this is very easy. And in fact, they look very much like on the picture. And if you think that, for example, the Gauss curvature is constant and positive, then there is no big mystery in this case that this part here looks like a multiple of the cosine function, which has been suitably translated. Okay, so as I said, the Toda equation, you can solve it explicitly. And in fact, the solution of this equation can be written like this. They depend on epsilon because the equation depends on epsilon, but also they also depend on a positive parameter, which I call lambda. And basically, lambda tells you exactly what is the slope of the solution at infinity. Right, so this is explicitly known. And the idea is that if you imagine that for all epsilon, you have a solution of this nonlinear equation, then at the end, what is going on is that you end up the part of the curve, which is in blue, converges to something which looks like this. And this is called, this is what we have called the bouncing Jacobi field. And the bouncing Jacobi field can be described as follows. So along your geodesic, so 0 is a point on the geodesic, and the last point is the length of the geodesic, you will find many points, S1, S2, and Sn. And for each of these points, in between 2 points, you have a solution of the Jacobi equation. And this solution has the property that it is equal to 1 at each of the points Sj, Sj plus 1, and so on. And moreover, what you want is that this solution satisfies this all these equalities here, namely that at each of these Sj, the left derivative and the right derivative, they have exactly opposite signs. Okay, so this is exactly like on the picture. So if you have a bouncing Jacobi phi with L and minimum, what you can do is that you can try to perturb it and insert here properly scaled version of the Toda equation. And then eventually, if you're lucky, you will be able to find this solution of the Jacobi Toda equation. Okay. Okay, so it turns out that this problem can be, so the main question is, can you find function phi solving all this system here? And in fact, you can give a variational framework. You can put this into a variational framework. So what you do is that you pick up along your geodesic endpoints, S1 to Sn, and on each of the interval Sj, Sj plus 1, you solve the Jacobi equation with boundary points equal to 1. And then what you do is that you cook up the sum of the Dirichlet energy of all these functions here. So now this is a function that only depends on S1, Sn, provided you can solve this equation along this interval. But let's imagine that this is okay. So you have a functional which we call Hn, which depends only on points S1, Sn. And what you can check is that critical points of this functional here, they give rise exactly, so you have to move the points S1, Sn, they give rise exactly to bouncing Jacobi field. So each time you have a critical point of this finite dimensional function, then you get a bouncing Jacobi field, and from this bouncing Jacobi field, you can build a solution of the Allen-Cahn equation. So at this stage, you might wonder if this is possible. And in fact, there are two very not so difficult lemmas. The first lemma says that if the Gauss curvature is positive along the geodesic, and if n, which is the number of points where this bouncing Jacobi field will take the value 1, if the number of points n is large enough, so the inequality is exactly this one. So if n is large enough, then there exists a bouncing Jacobi field with m minimum. And in fact, you can even prove that this bouncing Jacobi field is obtained by maximizing this energy Hn. And also you can check not so hard that if n is small compared to the value of the Gauss curvature, then there is no bouncing Jacobi field with m minimum. So you can check that these two inequalities, they don't come from nowhere. And in fact, if the Gauss curvature is constant, then you find that these are the best you can do, because you can do all computations explicitly with cosine functions. Okay, now I need to introduce the last definition. What is the index of a bouncing Jacobi field? Where, as I said, to get bouncing Jacobi field, you need to find critical points of a function, which I've called Hn. So by definition, we say that the index of the bouncing Jacobi field is exactly the index of the points S1, Sn as a critical points of my function Hn. Okay, so since my function Hn goes from Rn to R, then the index of bouncing Jacobi field is always between 0 and n. Okay, so now I need some assumptions, and the assumptions is I need to have a geodesic which is embedded, non-degenerate, closed, and I need phi to be a bouncing Jacobi field, but we can see that there are instances where we have bouncing Jacobi fields with n minimum. And with this hypothesis, what you get, so this is in dimension 2. The manifold you start with is a surface. And then what you get is that for all epsilon small enough, you can find a critical point U epsilon of the energy, of the Allen-Cahn energy, whose zero set, in fact, consists in two normal graphs, almost symmetric with respect to the geodesic gamma. And the zero set converges to gamma with multiplicity 2. And in fact, you can even compute the index of the solution of the Allen-Cahn equation. And it turns out that the index of the solution of the Allen-Cahn equation is given by the index of gamma. Well, this was quite natural because this was already the case in the first result I've told you about, the one with Ritoré, and to which you have to add the index of the bouncing Jacobi field plus n. And what is n? This is the number of minimum of my bouncing Jacobi field. Okay, so this result, this theorem says that in essence the result of Chodos and Mantoulidis doesn't work in dimension 2, and dimension 2 is very special because of this. Okay, so if you put everything together, what I have tried to so the result about the existence of bouncing Jacobi field and the theorem. So we know, for example, that there is existence of a bouncing Jacobi field in maximizing with points maximizing this function Hn. And in this case, this corresponds to critical points of the Allen-Cahn equation whose Morse index is equal to the Morse index of the geodesic plus 2 times the number of minimum of my bouncing Jacobi field. So this result provides solution of the Allen-Cahn equation whose Morse index is uniformly bounded as epsilon tends to 0. And what is interesting, in my opinion, is that there is a relation between not only the Morse index of the solution not only involves the Morse index of the geodesic, but also involves something else, which was pretty surprising when we discovered it. Okay, so I think I will stop here, and thank you for your attention, even if it's remotely.